Hello, New Harquahala Generating is honored to present an analysis on SCR catalyst performance loss. We will be looking into performance improvement options and the possible need to replace catalyst on units 1 and 2 prior to the 2012 operating season.
What is driving this critical effort? Catalyst sample analysis results from multiple service providers indicate that the catalyst has not retained sufficient enough reactivity to maintain stack emissions within site permitted limits. Site personnel become increasingly concerned about the risks and difficulty in controlling stack emissions, particularly during transient and startup conditions. Site personnel have been increasingly anxious about emissions control performance and believe something must be done to reduce the risk of an exceedance in 2012.
This presentation will explore the possible contributing factors to poor SCR performance and evaluate the most likely causes. We will investigate the accumulated data, evidence, answer any outstanding questions, and identify the best course of action. Fossil Energy Research Corporation, or FERCO, performed a comprehensive study on catalyst failure published in 2010 and concluded the four most probable issues pictured here. NHGC has evaluated CT and HRSG performance to determine if we can cost-effectively expect to extend catalyst life.
Over the next few slides, we will investigate each of the potential contributing factors to poor SCR performance. Let's start with maldistribution. NHGC has very little empirical data to confirm or deny any maldistribution problems. All HRSGs have variation in emissions distributions, as seen here in this diagram. Catalyst manufacturers typically build in enough reactivity to compensate for this. The difference in NOx distribution and velocity distribution usually varies between 8 to 15% built in. Haldor Topsoe Incorporated did an evaluation of some of NHGC's preliminary data and responded in October of 2011 with the belief that a temperature and or NOx ammonia maldistribution may exist, as seen in other similar HRSGs in the industry. These maldistributions may have been unseen when the catalyst had sufficient activity to compensate for these maldistributions until recently, as the catalyst has continued to decay. Given our current resources, it is difficult to prove that a maldistribution exists or does not exist. However, there are a few observations that can be established for the probability of maldistribution at Harquahala. An inspection of our HRSG reveals that NHGC has two important design considerations that aid in proper diffusion and distribution of exhaust flue gases. The first of which is flue gas diverters in a well-made two-bundle set in upstream of the CO catalyst. The second is the CO catalyst itself, just upstream of the SCR catalyst and AIG grid. Additional analysis shows that increased injection of ammonia sufficiently eliminates any reduced performance due to poor distribution of ammonia to NOx. By introducing enough ammonia with every catalyst channel to achieve maximum catalytic reaction, the overfeeding of ammonia can sufficiently eliminate any maldistribution issue between ammonia and NOx. This variable has helped in determining the probability of gross maldistribution problem.
NHGC looks forward for the opportunity to evaluate any maldistribution issues and to specifically tune the ammonia injection grid. To do this properly, we would need to install a comprehensive grid of 36 sample points on the outlet of the SCR catalyst, and then subcontract an analysis company to obtain the necessary data. To achieve proper AIG tuning is estimated to cost $208,000 for 2 units. An interesting point made in FERCO's catalyst study identifies that catalysts with low stack NOx requirements and higher ammonia slip allowances support greater maldistributions. These conditions support HRSG users with varying operational ranges and equipment configurations that may have an impact on the distribution of NOx over both daily and life cycle timeframes. From the same study comes a method to eliminate NOx maldistribution concerns by feeding more ammonia. NHGC has used this approach in the past to essentially rule out ammonia maldistribution. By feeding more ammonia and studying the data, NHGC has reinforced that catalyst performance issues are more dependent on temperature than ammonia flow, which does not support maldistribution concerns. NHGC does not currently advise any aggressive efforts to tune the AIG without replacing the catalyst due to evidence that supports good operation with adequate catalyst reactivity. Additionally, cost considerations, root cause analysis, and the likelihood of having to replace the catalyst anyway are also reasons not to support tuning efforts as a temporary fix.
NHGC is very confident that the possibility of flue gas bypassing the SCR has already been addressed in the past, and that all inspections and analysis support this confidence.
It is obvious and unanimous when looking at multiple lab reports and sample analysis that they show our catalyst is degraded towards and potentially past the threshold required to maintain stack emissions as designed. A trend of catalyst NOx conversion efficiency based on operational data collected from Unit 2 from 2008 through 2011 appears to agree and is congruent with these reports. So how have we continued to operate without an exceedance? Harquahala's real-world operating conditions are certainly more favorable than lab testing conditions, which are based on design and can be 10% higher than field conditions. It is the difficulty to control and maintain emissions and the dissipating margin from an emissions exceedance that NHGC is responding to in a proactive approach. We hope to proactively prevent the inability for NHGC to optimize our market position and current run profile due to an emissions control degradation and violation of an emissions limit. As Vice President of Environex points out in his combined cycle journal article on SCR performance, single sample testing can underestimate activity of the catalyst bed and prompt a decision to replace catalyst prematurely with negative cost impacts, or it can overestimate activity and leave you exposed to the possibility of exceeding permit emissions limits. We cannot rely on spot sampling alone. We must look at other metrics to make this determination. Note, the trend in blue is calculated efficiency based on historical operational data, which shows a similar trend to lab analysis. NOx removal efficiency can be a misleading figure when it is not viewed in the context of the determinant variables. Factors such as inlet NOx concentration, catalyst temperature, and ammonia flow play a big role in the observed catalyst efficiency. Let's explore some of these variables. This graph shows NOx removal efficiency versus ammonia flow. The results are as expected. NOx removal efficiency is a function of ammonia flow. If you need more conversion efficiency, feed more ammonia. This increase in ammonia flow has been the primary response Harquahala has made to continue operating with the depleting catalyst reactivity and has prevented exceedances over the past year. However, this approach is limited and can only provide temporary improvements in the conversion efficiency. Similarly, this trend shows the impact of inlet NOx on the conversion efficiency calculation. Higher inlet NOx being reduced to the same outlet concentration of 2 ppm will require more ammonia and yield higher removal efficiency percentages to achieve the same outcome as the lower inlet NOx concentrations.
Most of NHGC's observed difficulty occurs when catalyst temperatures are in the lower range of design, 600 to 625 degrees Fahrenheit. These observations are congruent with sample test results from the lab and operational data analysis, which shows insufficient remaining activity at lower temperatures. Catalyst deactivation, first noticeable at lower temperatures, appears to have the largest impact to NOx removal at this time. The scatter plot here shows NOx removal efficiency versus temperature for data collected in 2011. NHGC operates between 600 and 650 degrees Fahrenheit. These trends show our NOx efficiency as a function of temperature from 2008 to 2011 on Unit 2. The red line represents Hitachi Zosen's design NOx removal efficiency performance curve as expected. As you can see, NHGC's current operations fall well beneath design expectations, which conservatively allows for deviation from input parameters. Please note the cloud of risk. It is aptly named because the units operate within this temperature range for the first few hours after every startup. This is the most likely time frame of an emissions exceedance. This graph shows the history of ammonia flow, seen in orange, and the pounds of ammonia fed per ppm reduction in NOx, seen in green. It identified to NHGC that since 2008-2009, the unit has required increased ammonia flow and, more importantly, increased ammonia per ppm of NOx removal. One concerning observation that was identified corresponds with other trends that show 2009 as our best gas turbine emissions year. This graph shows that while we were able to respond with lower NOx emissions by feeding lower ammonia feed rates, the actual performance of the catalyst was requiring more ammonia flow per ppm of NOx removal, and the pounds of ammonia fed to remove NOx increased. This is seen as a big indicator of catalyst reactivity loss and corresponds well with the end-of-life observations made by the catalyst sampling companies. This graph also corresponds with and shows results of the efforts NHGC has made in 2010 and more so in 2011 to prevent overfeeding of ammonia, which helped to keep the pounds of ammonia fed per ppm of NOx reduction from increasing more rapidly. Did you know that catalyst does not deactivate linearly? Near the end of life, ammonia slip increases exponentially as the catalyst deactivates. Dan Ott, VP of Environics, provided examples and trends during the 2008 CTOTF conference. By overlapping Mr. Ott's ammonia slip curve from his article in CCJ, we can see a frightening resemblance in the increase of slip to our own data over the last 4 years.
Catalyst deactivation and replacement is disconcerting for units that have less than the equivalent of 2.5 years of total runtime logged. NHGC has information and sample results that indicate SCR catalyst degradation is caused from poor substrate materials used by Hitachi Zosen and is one of the main contributors to lost reactivity as the substrate materials delaminate. This was especially identified when Harquahala had lab tests conducted that proved trying to clean the catalyst would only make conditions worse, as seen in this graph of before and after cleaning performance test results. Another clear indicator on the catalyst material condition are these 3 photos, which show what the catalyst looked like new, before cleaning, and after cleaning. It also correlates well with the field observations that have repeatedly labeled Hitachi Zosen catalysts as extremely brittle. Also, when we compare the images of our catalyst with this conversion diagram, it is apparent that the pores and pathways through which the flue gas stream reaches active sites that enable the catalytic reaction are no longer available for mass transit on our catalyst. Both NOx and ammonia pass through the catalyst unreacted from their inability to reach active sites within the substrate. Progress Energy had similar frustrations with their Hitachi Zosen catalyst installed on their NIM units with 501G gas turbine technology. Quote, "We were not happy with the 6-year life we experienced with the original catalyst," states Todd Young, PE of Progress Energy. It is also interesting to note that during the past 18 months, Haldor Topsoe has replaced 6 NIM Hercigs with Hitachi Zosen catalysts. 4 of the units included APS Red Hawk, located just east of our facility, who reports having issues with and were severely limited by their catalyst since day 1. Over the last 2 weeks, NHGC has been taking a detailed look at SCR system performance, the gas turbine, and our operational procedures and data to better map out all factors that may be affecting NOx removal performance. NHGC has been thoroughly analyzing all areas in an effort to identify an avenue that would delay catalyst replacement in 2012. Over the next few slides, we will look at evaporative cooler's impact on gas turbine emissions, gas turbine potential for tuning emissions, gas turbine ramp set points and startup schedules and their resulting impact, and AIG SCR tuning and optimization options. One of the questions posed in our earlier discussion was, do evaporative coolers increase emissions when enabled? And if so, can we modify the current operational practice to enable these coolers later in the startup when our emission limit margins are greater? To answer this question, Ryan DeGraff is going to walk us through two similar starts on Unit 2, comparing operations between 2010 and 2011.
The first startup trend here is from July 2nd, 2011. During this start, you can see the evap coolers went into service at the peak of the gas turbine ramp. At the bottom of the trend, you can see the resulting NOx emissions during this time, and throughout the next few hours of operation range from 23 to 27 ppm. The second picture is the start on Unit 2, August 2nd, 2010. As you can see in the top trend, evap coolers go into service later in the startup. Looking at inlet NOx during the time frame when evap coolers are not in service, and comparing, we see the inlet NOx range from 20 to 24 ppm, and after evap coolers are placed in service, NOx is around 21 ppm. In this example, a direct comparison cannot be made between the ranges of inlet NOx, seen as the emissions are more of a function of normalized load than evap cooler status. However, we can note in 2010, when evaps went into service, NOx emissions fell within the range of what was produced when evaps were not in service. Another note can be made that emissions between these examples are respectively close given the number of variables that contribute to the observed concentration. The average concentrations are notably in the 20s for both starts, and as we will later see, represents the lowest emissions profile of the 501G fleet we have observed.
Let's look at a cold start on Unit 2, this time in July of 2009. On this trend, the data has been divided into sections to show when the unit is flagged online and when our online limits apply. This will be helpful to identify at what point and in which period the evap coolers are enabled and the resulting emissions are observed in relation to our emission limits for that period. In this example, evaporative coolers are in service shortly after the gas turbine ramp during the last flagged hour of startup. This is when the unit is online, but the startup emission limits continue to apply. When evap coolers are enabled, the direct impact to the SCR inlet conditions is a slight improvement of NOx emissions. This improvement is driven by the inlet temperature driving down the percent load, which drives IGV position and corresponds in improved NOx from the machine. NOx emissions from the gas turbine during the first hour, in which online emission limits apply, is about 19 ppm on average, while sitting at 76% load. Catalyst temperature at this time is 615 degrees in 2009. Note, in 2009, during our load hold of 30%, SCR inlet NOx is 36.6 ppm. When load increases after startup to 96% load, SCR NOx is about 30.5 pp. Let's look at a hot start on July 4, 2011, Unit 2. Evaporative coolers went into service during the first online hour. The impact was a reduction in load from 96 to 94% and a corresponding SCR inlet NOx reduction from 36 to 30 ppm. Inlet NOx increased as the CT was ramped for additional load from 94 to 96, which increased IGV position. The result was an additional 4.5 megawatts. This increase in megawatts increased fuel consumption and corresponding NOx emissions output from 30 to 36 ppm. Without evap coolers in service, the CT would have had higher NOx emissions at a higher load. Catalyst temperature during this hour is relatively higher than other starts because of the load percentage achieved in the first online hour. At 96% load, the catalyst temperature is 635 degrees Fahrenheit. The NOx conversion at this point is 93.6% due to the inlet NOx, catalyst temperature, ammonia flow, and catalyst activity at this temperature. NOx is being reduced from 36 ppm to 2.3 ppm at this hour. It is interesting to note at 88% load, the catalyst temperature is 619 degrees Fahrenheit. and at this temperature it takes 24.8 pounds of ammonia to remove 1 ppm of NOx. However, when the catalyst temperature reaches 635 degrees at 96% load, it only takes about 17.6 pounds of ammonia to remove 1 ppm of NOx. This shows significantly improved catalyst performance at the higher temperatures and compensates for the 36% rise in inlet NOx due to the load increase.
When assessing the impact of Evap Cooler operations on NOx emissions from the gas turbine, it is evident that Evap Coolers decrease the temperature of the air entering the gas turbine inlet. This decrease in temperature corresponds to a decrease in the load percentage of the engine. As the current load percentage calculation changes as a function of inlet temperature, IGV position changes to match the load percentage as determined by the IGV load curve. Our analysis notes that this change translates in a slight decrease in emissions from the gas turbine in all cases reviewed. It should also be noted that if Evap Coolers are left out of service, gas turbine output is limited in terms of megawatts, and the unit reaches higher loads and corresponding higher emissions as a result. Evap Coolers reduce our instantaneous load percentage, causing an IGV position change that favors decreased NOx emissions. To summarize all the data and trends we have looked at from year to year, unit to unit, the Evap Coolers have only a slight impact on gas turbine emissions, and that impact appears to favor a decrease in SCR inlet emissions.
September 6, 2011, by all measures, was an ideal start for Unit 2. Ammonia flow during the startup was controlled to about 220 pounds an hour, optimizing our vaporizer outlet temperature and SCR catalyst temperature during this window to prepare for the increased load on the SCR system during the ramp. As the unit was ramped out of startup, combustion turbine emissions were healthily below 30 ppm, with EVAPs in service shortly after the CT status swapped from startup to online. However, despite the optimized SCR inlet NOx conditions and optimized ammonia flow, NHGC struggled to get NOx stack emissions below 3.5 ppm for the first hour online. This first hour is when gas turbine load is balanced with heat into the HRSG to optimize steam turbine margins. Catalyst efficiency during this time was significantly reduced as a function of temperature, putting NHGC in a difficult position over the next 2 hours. As the steam turbine came online and gas turbine was ramped per the schedule, catalyst temperatures increased to just enough to minimize the increased SCR inlet NOx resulting from the load increased. As the third hour rolled past, NHGC's NOx average for the past 3 hours came just shy of the 2.5 ppm limit. The current condition of the catalyst is leaving less and less margin for NHGC's 3-hour rolling ppm limit and 1 hour pound per hour limit for NOx, and puts us at risk for violating these limits despite historical and recent efforts to optimize the SCR system, gas turbine emissions, and ramp schedules. As seen on July 4, 2011, ramping the unit to a higher load during the first hour can significantly improve the SCR's performance and compensate for the higher NOx produced at these loads. This practice is, however, a short-term solution that Harquahala cannot depend on reliably. As the catalyst continues to lose its ability to convert the available NOx and ammonia as designed, we will be put into a position that leaves no margin for error. Despite our best efforts, upsets and conditions that are unfavorable to the aging SCR system are expected despite our proactive prevention activities.
Great questions posed during earlier SCR discussions were, are 2011 emissions higher than in the past, possibly complicating this issue? And can we tune the gas turbine to decrease NOx emissions, if not in all areas, at least in the first hours of operation when limits apply? A decrease in emissions during the first few hours of startup would put less demand on the aging and poor performing catalyst and potentially allow NHGC to operate in 2012 with minimized risk. To further evaluate our NOx removal performance, NHGC mapped out SCR inlet NOx history. The results show that engine performance has been fairly steady around 20 to 30 ppm range over the last few years, with 2009 being our best year in terms of SCR inlet NOx. Other G users were contacted to determine if NHGC might be experiencing higher than normal NOx emissions. What we found was the opposite, with NHGC appearing to have appreciably lower gas turbine NOx emissions than its counterparts.
NHGC combustion turbines currently tuned with an emphasis placed on NOx emissions performance at all loads. To support RADA testing performance results, reductions in base load NOx emissions have been targeted. NHGC worked with Gary Hildebrandt in an effort to improve SCR catalyst warm-up during startup without negatively impacting or increasing CT NOx emissions. Gary prescribed some changes that were made September 2nd. NHGC is committed to finding creative ways to reduce the demand on the SCR systems through reduced CT emissions to prevent an emissions limit violation. However, current operating performance is very favorable and leaves NHGC little room for improvement. Expectations are that we can improve things slightly, but not enough to compensate for catalyst reactivity loss. Below is a summary of individual tuning events which included efforts to prevent high temperature unloads, megawatt swings, nuisance alarms, base load NOx reductions, and SCR temperature optimization.
As we have seen, gas turbine emissions are significantly impacted by the output of the turbine. If our engines are tuned for optimum output for our technology, are there any other operational changes we can make to minimize the load on our SCR catalyst when it is most critical? Let's take a look. Harquahala does not experience any issues or situations that could lead to emission exceedances prior to reaching 50% load and achieving the online status for the gas turbine. Spikes in NOx emissions below 50% load are consistent and reoccurring, with B-stage fuel gas emission close to 40% load, followed by a quick drop when C-stage gas comes in around 45% load, and the fuel gas breeder goes into service. After achieving online status and during the ST warm-up phase of the unit startup is when things become most difficult. Because of the 501G technology and control area requirements, NHGC has designed and optimized the startup load schedules to minimize total startup time. Efforts have had significant impacts on the ramp and start schedules for the ST, but have negligible impact on the CT side of the start schedule. Different load set points can have a dramatic effect on the stack emissions performance during this ST warm-up time frame. Until recently, NHGC has targeted the best CT load to ensure ST warm-up is achieved by establishing ideal steam conditions. Recently, due to emissions issues on occasion, NHGC has attempted to modify load set points during startup to specifically address stack emissions and avoid an exceedance. Evidence so far points to better stack emissions by rapidly increasing SCR catalyst temperature as fast as possible versus finding the load with the lowest possible SCR inlet NOx. Finding load set points to optimize stack emissions has the potential to increase warm-up stresses on the ST and negatively impact startup schedules. NHGC has very little experience operating the fuel gas heater outside of the prescribed Siemens recommendations. In one particular case, the heater failed to go in service, and NHGC noted a negative impact to CT emissions and hence believes that leaving the heater out of service until later in the startup will make controlling emissions more difficult. NHGC sees very little room to further adjust startup schedules to improve stack emissions. We will continue to make real-time adjustments and decisions during startup to prevent an emissions exceedance, which includes targeting specific load set points and shutting down if necessary.
As previously discussed and now reiterated, there may be room for AIG SCR system fine-tuning for maldistribution issues. In light of everything else we have looked at, NHGC expects this to have minimal impact on SCR performance, and we do not believe that this is a viable solution to delay catalyst replacement at this time. However, to prevent maldistribution from impacting the performance of our SCR skid, whether new, old catalyst exists, AIG tuning and measurement may provide long-term cost benefits and extend longevity of a replacement catalyst.
NHGC has maintained a library of references and resources related to the SCR catalyst performance and analysis, as pictured here. All information is easily accessible and available upon request.
While building this presentation, NHGC received the most recent catalyst sample results. As expected, the results are not favorable with regard to continuing operations without the risk of an emissions exceedance. In summary, NHGC would like to express the urgency that exists with the need to schedule catalyst replacements on Units 1 and 2. Our effort is not to generate a current crisis, but to prevent one in the future. The primary and initial goals of maximizing or extending the useful life of the current Hitachi-Zosen catalyst was useful and informative, but yielded disappointing results. We believe the only correct course of action at this time may include multiple lines of effort, but cannot preclude the expedited purchase and installation of new SCR catalysts prior to 2012 operating season.